You are not standing still, even as you sit here, reading these words. The space between galaxies is stretching, not drifting, not flowing like air or water, stretching quietly, relentlessly, carrying entire clusters of stars away from one another. This expansion is not subtle. It is measurable. It has a number, and that is where the trouble begins. When astronomers try to measure how fast the universe is expanding, they do not get one answer. They get two. One method says the universe is expanding at about 67 kilometers per second for every megaparsec of distance. Another says the rate is closer to 73 kilometers per second per megaparsec. The difference may sound small. It is not. That gap is large enough to matter, precise enough to persist, and stubborn enough to refuse explanation. Two numbers, one universe. If this were a simple mistake, it would have disappeared years ago. Better telescopes would have corrected it. Improved statistics would have smoothed it out. Independent teams would have converged on a single value. That did not happen. Instead, the more carefully the universe is measured, the more clearly the disagreement stands. This is not a failure of sloppy science. It is the opposite. The conflict emerges only because modern cosmology has become extraordinarily precise. Every decimal place sharpened the tension. Every improvement made the mismatch harder to ignore. The number in question is called the Hubble constant, often written as H0. Despite the name, it is not truly constant in time. It describes the current rate at which space itself is expanding, how fast galaxies recede from one another as a function of distance. Think of it as the universe's present-day heartbeat. Measure it one way, by reading the faint afterglow left over from the early universe, and the heartbeat is slow and steady. Measure it another way, by carefully building a ladder of distances to nearby galaxies, and the beat quickens. Both measurements are made with care. Both rely on decades of accumulated knowledge. Both are internally consistent. They simply do not agree. This disagreement is known as the Hubble tension. It is one of the most uncomfortable problems in modern cosmology because it sits at the intersection of confidence and uncertainty. The physics used to interpret the measurements works beautifully elsewhere. The observations themselves are among the best humanity has ever produced. And yet, when asked a basic question, how fast is the universe expanding right now? The cosmos gives two answers and offers no explanation. At first glance, the situation feels almost trivial. Surely one method must be slightly wrong. Perhaps dust dims stars in a subtle way. Perhaps distant galaxies are messier than expected. Perhaps early universe physics has been oversimplified. Those possibilities have been examined repeatedly. Astronomers have remeasured the same stars in different wavelengths. They have refined calibrations, corrected for crowding, accounted for chemical composition, cross-checked instruments, and invited rival teams to audit their work. On the other side, cosmologists have tested the assumptions baked into the interpretation of the universe's oldest light, asking whether small changes could reconcile the numbers. They could not. The tension persists, not because scientists are careless, but because the universe seems unwilling to be pinned down by a single story. To understand why this matters, it helps to appreciate what these two numbers represent. They are not pulled from abstract equations alone. They are anchored in radically different views of reality. One number is inferred from a time when the universe was young, less than 400,000 years old before stars, galaxies, or planets existed. It is extracted from patterns in ancient radiation that fills all of space, a relic from an era when matter and light were still tightly coupled. The other number is assembled from the present-day universe, built step by step from nearby stars whose brightness rises and falls with clockwork regularity, extended outward through exploding stars visible across cosmic distances. One method listens to the universe as it was. The other listens to the universe as it is. If both are correct, then something has changed along the way. That implication is unsettling. Modern cosmology rests on a framework that has been astonishingly successful. It explains the formation of galaxies, the abundance of light elements, the structure of the cosmic web, and the detailed patterns seen in the oldest light in the universe. It requires only a handful of ingredients: ordinary matter, dark energy, and the laws of gravity as currently understood. The Hubble tension does not overthrow this framework outright, but it strains it. It suggests that something small but significant may be missing an effect that mattered in the early universe and faded away, or a subtle interaction that alters cosmic expansion in ways not yet fully captured. What makes this problem especially compelling is that it cannot be dismissed by appealing to ignorance. This is not a gap where data is scarce. It is a disagreement that survives abundance. In science, uncertainty usually shrinks with better information. Here, better information has made the problem sharper. That is why the Hubble tension has become more than a technical detail discussed in specialist journals. It has become a philosophical challenge. It forces a confrontation with a deeper question. When measurements disagree, how do you decide which story reality is telling? The answer is not to choose sides hastily. Cosmology advances by patience, not by proclamation. Every proposed solution must fit not only this discrepancy, but everything else we already understand about the universe. A fix that solves the tension but breaks other successes is no solution at all. So the numbers remain: 67, 73. They sit uncomfortably close, separated by just a few kilometers per second per megaparsec, yet divided by implications that stretch across billions of years. They remind you that the universe is not obligated to be simple, even when its behavior can be written as a single number. Standing at this point, you are not witnessing a crisis. You are witnessing a boundary, a place where knowledge stops being smooth and starts becoming interesting. The expansion of the universe is not just a fact to be memorized. It is an ongoing measurement, a dialogue between observation and theory. And right now, that dialogue is unresolved. Two numbers remain on the table, and the universe, for the moment, says nothing more. When you hear that the universe is expanding, the image that often comes to mind is simple: galaxies flying outward into empty space, like fragments from an explosion. It feels intuitive. It is also wrong in a subtle but important way. Cosmic expansion does not describe objects moving through space. It describes space itself changing. This distinction matters, because the number astronomers measure, the one that disagrees so stubbornly, does not track speed in the everyday sense. It tracks how distance behaves when the stage on which everything sits is stretching. Imagine marking two dots on the surface of a balloon. As the balloon inflates, the dots move apart even though neither dot is crawling across the rubber. The surface between them is what grows. The farther apart the dots are to begin with, the faster their separation increases, not because they are trying to escape each other, but because the surface beneath them is expanding. The universe behaves in a similar way, except the surface is three-dimensional space itself. When astronomers say a galaxy is receding at thousands of kilometers per second, they are not claiming it is firing its engines. They are describing how the metric of space changes with time. Distance grows, light stretches, wavelengths lengthen, the geometry evolves. The quantity that captures this behavior is the expansion rate at the present moment, commonly called the Hubble constant. But the name hides complexity. This number does not tell you how fast a single galaxy is moving. It tells you how much additional separation appears per unit distance because of expanding space. In practical terms, it answers a specific question. For every fixed amount of distance in today's universe, how much farther apart will two objects be 1 second from now? That is why the unit looks strange. kilometers per second per megaparsec. Speed divided by distance. It is not a velocity in the usual sense. It is a relationship. If two galaxies are separated by 1 megaparsec, about 26 million light-years, the expansion rate tells you how fast that separation grows. If they are 10 times farther apart, the increase in separation is 10 times larger. The rule scales with distance. This scaling is not a coincidence. It is the signature of uniform expansion. At small scales, the effect is invisible. Inside galaxies, gravity overwhelms expansion. Atoms do not drift apart. Solar systems do not unravel. Even galaxy clusters can remain bound. Cosmic expansion reveals itself only across truly vast distances, where gravity no longer dominates the average behavior of matter. This is why the measurement is so challenging. You cannot place a ruler across the universe. You have to infer expansion by observing how light changes as it travels across space that is itself evolving. When a galaxy's light reaches you, its wavelength is stretched. Blue light shifts toward red. This is known as redshift. But redshift alone does not tell you the expansion rate. It tells you that expansion happened while the light was in transit. Not how fast space is expanding right now. To measure the current expansion rate, you need two things at once: redshift and distance. Distance is the harder of the two. Redshift can be measured with exquisite precision. Distance must be constructed indirectly, step by step, using objects whose intrinsic brightness or size is known. This is where the complexity and the vulnerability enters the story. The expansion rate you infer depends on how well you understand your distance indicators. If your distances are slightly off, the slope of the expansion relationship changes. The number shifts. But there is another layer that makes the Hubble tension more profound. The expansion rate is not fixed across cosmic history. In the past, the universe expanded faster or slower depending on which ingredients dominated its energy content. Early on, radiation mattered. Later, matter shaped the expansion. Today, dark energy appears to drive an accelerated stretching of space. So when astronomers infer today's expansion rate from the early universe, they are not measuring it directly. They are extrapolating. They take a snapshot of the universe when it was young, then evolve it forward using the known laws of physics to predict what the expansion should be today. This means the early universe method measures the expansion rate indirectly, filtered through a model of cosmic evolution. The late universe method does the opposite. It measures distances and redshifts in the nearby universe and reads the expansion rate off directly, with minimal assumptions about what happened billions of years ago. Both approaches are valid. Both are elegant. They simply answer the same question from opposite ends of time. If the universe followed the expected rules perfectly, both paths would converge on the same present-day value. They do not. This raises a subtle question about what, exactly, cosmic expansion measures. Is it merely a geometric property of space, or is it also a diagnostic of the universe's contents and interactions? The expansion rate is sensitive to everything that influences gravity on the largest scales. Ordinary matter slows expansion. Dark matter shapes structure. Dark energy accelerates the stretching of space. Even small, early contributions, brief episodes of additional energy, can leave an imprint that persists into the present. That is why a disagreement in the expansion rate is not a trivial bookkeeping issue. It is a clue that something about the cosmic recipe may be incomplete, yet it would be a mistake to imagine the universe choosing one number over another. Nature does not negotiate with measurements. The conflict exists only in our descriptions, not in reality itself. What the Hubble tension exposes is the difference between measuring a process directly and inferring it through a chain of reasoning. Both are powerful. Both can fail in different ways. Cosmic expansion. Then, is not a single phenomenon captured by a single experiment. It is a relationship stitched together from light, distance, time, and theory. The number that describes it is not merely observed, it is interpreted. This is why the disagreement feels so unsettling. It is not about motion, it is about meaning, about how confidently you can translate what you see into what is happening. In everyday life, disagreement between measurements usually points to a faulty instrument. In cosmology, it can point to a deeper issue, a mismatch between assumptions and reality. Cosmic expansion measures how the universe grows, but it also measures how well you understand the rules governing that growth. And when those rules produce two answers instead of one, the question is no longer just how fast space is stretching. The question becomes how much of the story has already been told and how much remains hidden in the space between the numbers. If you could measure distance in the universe the way you measure it on Earth, cosmology would be easy. You would point, measure, record, and move on. But the universe does not allow that. There is no cosmic tape measure, no reference wall, no fixed background against which everything can be lined up. Distance in astronomy is never touched, never crossed, never directly experienced. It is inferred carefully, indirectly, and always with an element of trust. This is why distance is the most fragile quantity in the science of the cosmos. You can measure time with clocks. You can measure mass through gravity. You can measure light with extraordinary precision. But distance, especially over millions or billions of light years, must be reconstructed from clues. And every clue depends on assumptions. When you look at a star in the night sky, your eyes receive light that may have been traveling for years, centuries, or millennia. The star could be close and dim, or distant and brilliant. From brightness alone, you cannot tell which is which. That ambiguity never goes away. Astronomy begins with a fundamental problem. Light carries information, but it does not carry a label saying how far it traveled. To convert light into distance, you must know something intrinsic about the source, its true brightness, its size, or some physical behavior that can be relied upon. Without that, distance remains unknowable. This is why astronomers do not measure distance in one step. They build it. They assemble distance the way you would cross a river, by stepping stones. Each stone must be solid enough to stand on, because every step depends on the one before it. If a single stone shifts, the entire crossing becomes uncertain. This construction is known as the distance ladder. At the bottom of the ladder are methods that rely on geometry alone. They are the most secure, because geometry does not care about astrophysical complexity. But geometry has limits. Its reach is short. Once geometry fails, astronomers climb upward using objects whose properties have been calibrated by closer measurements. Stars that pulse, explosions that shine with predictable intensity, patterns that repeat with reliable regularity. Every rung extends reach. But each extension introduces vulnerability. A tiny error at the bottom becomes a noticeable shift higher up. A small bias at one rung propagates outward. By the time distance estimates reach hundreds of millions of light years, even a 1% uncertainty can alter conclusions about the universe itself. This fragility is not a flaw of poor technique. It is the unavoidable cost of trying to measure something vast from a single point inside it. Distance is especially treacherous because it rarely announces its own uncertainty. You do not see the error directly. You infer it later, when two independent methods disagree, or when the universe refuses to behave as predicted. In the context of cosmic expansion, distance is everything. The expansion rate is determined by comparing how fast galaxies appear to recede with how far away they are. The slope of that relationship depends entirely on the distance scale. Stretch the scale slightly, and the expansion rate shifts. Compress it, and the rate changes again. Redshift can be measured with astonishing accuracy. Distance cannot. This imbalance is crucial. When two methods produce different expansion rates, the first place scientists look is distance, not because distance is wrong by default, but because it is where uncertainty hides most effectively. Distance errors can masquerade as profound discoveries. They can also conceal real physics beneath layers of calibration. Consider how indirect the process really is. You observe a star. You measure its apparent brightness. You assume a true brightness based on a model or a known relationship. From the difference, you infer distance. That distance calibrates another object farther away. That second object calibrates something farther still. By the time the measurement reaches cosmological scales, the original geometric certainty has been transformed into a chain of inference, and yet, this method works remarkably well. The distance ladder has allowed humanity to map galaxies, discover the expansion of the universe, estimate its age, and reconstruct its history. It is one of the greatest achievements of observational science, but it was never designed to answer questions with absolute certainty. It was designed to answer them progressively. That distinction matters when disagreements arise. Distance also suffers from a psychological trap. Humans instinctively trust numbers that feel concrete, a length, a brightness, a scale. But in astronomy, those numbers are abstractions layered on top of interpretation. A star's brightness depends on dust, on composition, on environment, on subtle physical effects that may change with time or location. Each factor must be understood well enough to be corrected for, or at least bounded. This is why distance measurement is as much about understanding stars as it is about geometry. You cannot measure distance without knowing the nature of the objects you use as rulers. And nature is rarely simple. Stars evolve, galaxies collide, environments vary. What works cleanly in one region of space may behave slightly differently in another. The ladder must be constantly rechecked, recalibrated, and challenged. This constant scrutiny is not a weakness. It is the engine of progress. The Hubble tension emerges precisely because distance measurement has reached a level where different methods can now challenge each other. For the first time, astronomers can ask whether their distance scale is truly universal or subtly distorted. That question cuts deep. If distance has been misjudged, the expansion rate shifts. If the expansion rate shifts, the inferred age and size of the universe shift as well. Entire narratives must be revisited, but if distance is correct and still the numbers disagree, then the implications go far beyond measurement. They point toward the behavior of the universe itself. This is why distance sits at the heart of the problem. It is not merely a number on a chart. It is the bridge between observation and meaning, between what light tells you and what reality is doing. In astronomy, you never measure distance for its own sake. You measure it to understand motion, structure, history, and fate. Distance is the scaffolding upon which cosmic stories are built. When that scaffolding is questioned, the entire structure feels unstable, not because it is collapsing, but because its assumptions are being examined. Distance remains the hardest quantity in astronomy, not because scientists lack skill, but because the universe offers no shortcuts. Every measurement is earned, every scale is negotiated, and when the universe presents two expansion rates that refuse to reconcile, the first question is not which number is wrong. It is whether the distances we trust are telling the whole truth or only the part we have learned how to hear. Before astronomers could measure the universe, they first had to solve a much smaller problem: how to measure anything beyond Earth at all. For centuries, the stars appeared fixed. They rose, they set, they traced circles in the sky, but they did not seem to move relative to one another. This stillness was comforting, but it was also deceptive. It suggested permanence where none existed. and it hid depth behind a flat illusion. The breakthrough came not from building larger telescopes, but from learning how to shift perspective. Parallax is a simple idea, familiar even in everyday life. Hold your thumb at arm's length and close one eye, then the other. Your thumb appears to jump against the background. The closer your thumb is, the larger the jump. The farther it is, the smaller the shift. Your brain uses this effect constantly to judge distance. Astronomers realize that nature provides a similar opportunity if you are willing to wait. As Earth moves around the Sun, your viewpoint changes by millions of kilometers. A nearby star should appear to shift slightly against the distant background of more remote stars. Measure that tiny angular change, and geometry does the rest. No assumptions about stellar physics are required. No models of brightness or composition. Just angles and triangles. In principle, parallax is the cleanest distance measurement imaginable. In practice, it is brutally difficult. The shifts involved are unimaginably small. Even the nearest stars move by less than a single arcsecond, an angle smaller than the width of a human hair seen from several meters away. For stars farther still, the shift shrinks beyond the limits of detection. For centuries, astronomers searched for stellar parallax and failed. This failure was not a mistake. It was a clue. The stars were not merely distant, they were staggeringly far away. When the first reliable parallax measurements were finally made in the 19th century, they did more than provide distances. They shattered assumptions about scale. The universe instantly became deeper than anyone had imagined. From this geometric method emerged a new unit, the parsec. A parsec is defined as the distance at which a star shows a parallax shift of 1 arcsecond as Earth moves from one side of its orbit to the other. It is not an intuitive unit. It is not based on kilometers or miles. It is built directly from the act of measurement itself. 1 parsec equals about 3.26 light-years. This unit carries a quiet philosophical weight. It encodes the fact that distance in astronomy is not something you touch, it is something you infer from motion and perspective. A parsec is geometry turned into language. Parallax-based distances form the foundation of all cosmic measurement. They are the first rungs of the distance ladder, anchored in nothing more than Earth's orbit and the rules of triangles. But their reach is limited. As stars grow more distant, their parallax angles become too small to measure reliably. Even with modern instruments, parallax fades into noise beyond a few thousand light-years. For the wider universe, galaxies, clusters, cosmic structure, parallax alone is insufficient. This limitation is not a failure, it is a boundary. Within that boundary, parallax distances are trusted above all others. They calibrate every method that follows. They are the reference points against which other cosmic rulers are judged. If parallax were wrong, the entire ladder would lean. That is why modern astronomy has invested enormous effort into refining parallax measurements. Space-based observatories removed atmospheric distortion. Detectors became more sensitive. Statistical techniques improved. Each advancement tightened the foundation, and yet, even at its best, parallax does not reach very far. This creates a tension at the heart of astronomy. The most reliable method is also the most limited. To go farther, you must leave pure geometry behind and accept astrophysical assumptions. But before those assumptions enter the story, parallax teaches an essential lesson. It reveals that distance is not absolute, it is relational. You do not measure how far a star is in isolation. You measure how its apparent position changes relative to others as your own position shifts. Distance emerges from comparison, not from direct contact. This idea echoes throughout cosmology. Every distance you will encounter, every light year, every megaparsec can be traced back, ultimately, to this humble geometric effect. Even when the methods grow more elaborate, The logic remains the same. Observe change. Infer scale. Parallax also reshapes intuition. It forces you to confront how small Earth's orbit is compared to interstellar space. A baseline of 2 astronomical units, about 300 million kilometers, barely produces a measurable shift for the nearest stars. That fact alone reframes humanity's place in the cosmos. The stars are not points on a dome. They are scattered across a volume so vast that Earth's motion becomes almost irrelevant. This realization did not arrive with drama. It arrived with patience, careful observation, and acceptance of uncomfortable numbers. It marked the moment when the universe stopped being a backdrop and became a 3-dimensional structure. Parallax does not explain galaxies. It does not reveal cosmic expansion. It does not answer philosophical questions about origin or fate. But without it, none of those questions could be asked meaningfully. It is the quiet ruler that measures nothing grand directly, yet supports everything grand indirectly. In the context of the Hubble tension, parallax occupies a special role. It is the starting point for the distance ladder used to measure the local expansion of the universe. If parallax distances are biased even slightly, the error propagates upward. That possibility has been examined with relentless scrutiny, not because parallax is suspected of being wrong, but because it is too important to leave unquestioned. The first cosmic rulers were simple in concept and demanding in execution. They did not rely on exotic physics or speculative theory. They relied on patience, geometry, and the willingness to accept that the universe is far larger than comfort allows. Parallax and parsecs do not give you the universe. They give you a place to stand, and from that place, small, moving, and uncertain, you begin the long task of measuring everything else. Parallax gave astronomers a place to stand. Cepheid stars gave them a way to move forward. Once geometry reached its limit, distance measurement faced a dilemma. The nearby stars could be measured cleanly, but the universe did not end there. Beyond a few thousand light-years, parallax fades into uncertainty, and the sky becomes crowded with objects too far away to yield their depth through angles alone. To go farther, astronomers needed something different, not a ruler made of geometry, but a ruler made of behavior. They found it in stars that breathe. Cepheid variables are stars whose brightness rises and falls in a steady, repeating rhythm. They do not flicker randomly. They pulse, expand, contract, brighten, dim, again and again, with astonishing regularity. At first, these pulsations seemed like curiosities, stellar quirks with no obvious use. But hidden within their rhythm was a pattern so precise that it would reshape cosmology. The key discovery was simple, yet profound. The period of a Cepheid's pulsation is directly related to its true luminosity. Stars that pulse slowly are intrinsically brighter than stars that pulse quickly. This relationship is universal. Measure how long a Cepheid takes to complete one cycle, and you know how luminous it truly is. Once you know how bright a star really is, distance becomes accessible. If a star appears dim but is known to be luminous, it must be far away. If it appears bright and is known to be faint, it must be close. The difference between apparent brightness and intrinsic brightness reveals distance. This was the missing link. Cepheids transformed distance measurement from a geometric trick into a scalable method. They allowed astronomers to step beyond parallax without abandoning rigor. The stars themselves became calibrated beacons, cosmic lighthouses scattered across space. But this transformation did not happen instantly. The discovery of the Cepheid period luminosity relationship emerged quietly, almost anonymously, from careful analysis rather than bold theory. It was born not in an observatory dome, but in rows of photographic plates examined one by one. The importance of the discovery was not recognized immediately. At first, Cepheids were simply a new class of variable stars. Only later did astronomers realize that they offered something unprecedented. A standard candle bright enough to be seen across interstellar and even intergalactic distances. Once this realization took hold, the universe changed scale again. Cepheids could be observed far beyond the reach of parallax, first within the Milky Way, then in neighboring galaxies. Each detection extended the cosmic map outward, rung by rung. This is how the distance ladder was born. The ladder is not a single measurement. It is a hierarchy. Parallax calibrates Cepheids. Cepheids calibrate brighter objects. Those brighter objects reach still farther. Each rung depends on the stability of the one below it. Cepheids occupy a privileged position on this ladder. They are the first astrophysical rulers objects, whose distances can be inferred from their physical properties rather than pure geometry. That privilege comes with responsibility. Cepheids are not identical. Their behavior can be influenced by chemical composition, age, and environment. Dust can dim their light. Crowded stellar fields can blur measurements. Subtle biases can creep in unnoticed. This is why Cepheids have been studied obsessively. Astronomers observe them in multiple wavelengths to reduce the effects of dust. They compare Cepheids in different environments to test consistency. They recalibrate distances whenever parallax measurements improve. The goal is not perfection, but robustness. Every improvement tightens the ladder. Cepheids also carry a deeper lesson about how astronomy progresses. They show that the universe can be measured not only by structure, but by rhythm. Time becomes a proxy for distance. A pulse becomes a ruler. This inversion is elegant. You do not measure how far the star is directly. You measure how long it takes to change and infer distance from that regularity. It is a reminder that physical laws can be repurposed in unexpected ways. With Cepheids, the Milky Way stopped being the entire universe. Distances to nearby galaxies became measurable. The fog that once flattened the sky began to lift. Depth emerged where there had been only pattern, but the ladder remained fragile. Cepheids do not exist everywhere. They are massive stars with limited lifespans. They appear in regions of active star formation, not in every galaxy. Beyond a certain distance, even they fade from detectability. This limitation forced astronomers to search for even brighter rulers, objects visible across hundreds of millions of light-years. Cepheids would calibrate those next steps, but they could not replace them. Still, without Cepheids, the ladder would have no middle. They bridge the intimate scale of stellar neighborhoods and the grand scale of galaxies. They connect geometry to cosmology. They anchor the local universe to the distant one. In the context of the Hubble tension, Cepheids play a central role. They are the backbone of the local measurement of cosmic expansion. If their distances are biased, the expansion rate inferred from nearby galaxies shifts. If they are sound, the tension points elsewhere. This is why Cepheids are not just stars in this story. They are witnesses. Their steady pulses carry information across millions of years and trillions of kilometers. They encode distance in time, and by doing so, they allow the universe to be measured one rung at a time. Cepheid stars did not solve the universe. They did something quieter. And perhaps more important, they made the universe measurable. And once something becomes measurable, it becomes vulnerable to scrutiny, to disagreement, and to discovery. There are moments in science when the universe does not change, but everything you believe about it does. This was one of those moments. At the beginning of the 20th century, the universe was still thought to be modest, vast by everyday standards. Yes, but bounded. The Milky Way was considered the entirety of existence, a single island of stars floating in darkness. The faint, misty smudges scattered across the sky were debated endlessly. But most astronomers assumed they were small, nearby clouds part of our own galaxy. They were called spiral nebulae. No one knew what they were. Some thought they were star-forming regions. Others imagined they might be solar systems in the making. A few speculated that they were island universes, galaxies like our own, but there was no proof. Distance was the missing piece. Without it, scale remained guesswork. Then came a telescope perched high above the haze of Earth's atmosphere, and a man willing to trust what the data said, even when it contradicted everything that came before. Using the largest telescope of its time, Edwin Hubble studied one of these spiral nebulae, Andromeda. To the naked eye, it is a faint blur. Through a powerful telescope, it becomes a dense field of stars, tangled in spiral arms. Hidden among those stars were Cepheid variables. Hubble identified them carefully, patiently, one by one. He measured their pulsation periods. He calculated their intrinsic brightness. Then he compared that brightness to how dim they appeared from Earth. The result was unambiguous. Andromeda was not nearby. It was not a cloud within the Milky Way. It was far beyond the outermost stars of our galaxy, so far that it could only be another galaxy entirely. In a single measurement, the universe doubled in size. The Milky Way was no longer everything. It was one among many. This was not a gradual realization. It was a sharp fracture in understanding. The sky, once thought to be a dome of stars, became a deep ocean filled with distant archipelagos of light. Galaxies were not rare exceptions. They were the basic units of the universe. With that realization came a second, even more unsettling discovery. Hubble did not stop at measuring distances. He compared those distances to the redshifts of galaxies, the stretching of their light as it traveled through space. What he found was a pattern that no one expected. The farther a galaxy was, the faster it appeared to be moving away. Distance and recession were linked. This was not a random scatter. It was a straight line, a rule. Space itself was expanding. The universe was not static. It was not eternal and unchanging. It was dynamic, evolving, stretching in every direction at once. This idea did not emerge from theory first. It emerged from observation. The mathematics would follow. The philosophical consequences would take decades to sink in. At the time, even Albert Einstein was uneasy. His equations allowed for an expanding universe, but he had introduced a correction to keep space stable. Hubble's data made that correction unnecessary and uncomfortable. The universe, it seemed, had a history. Hubble's law was simple in form, but radical in implication. It tied velocity to distance. It suggested a beginning. If you rewind expansion far enough, everything converges. Galaxies draw closer. Space shrinks. The idea of a cosmic origin moved from speculation into scientific territory, but Hubble's work carried another, quieter transformation. It redefined humanity's position. Before, you could imagine standing near the center of everything. After Hubble, that idea dissolved. Expansion looks the same in all directions. Every observer sees galaxies receding. There is no special vantage point, no cosmic center you can occupy. You are not standing at the edge or the middle. You are simply inside. The universe did not just grow larger, it became stranger. Distance now meant more than separation. It meant time. Looking farther meant looking deeper into the past. Galaxies at extreme distances were not only far away, they were younger, less evolved, seen as they once were. Space and history intertwined. Hubble's measurements did not answer every question. They raised new ones. How fast was the expansion? Was it slowing down? Would it reverse? What forces controlled it? But the scale of the conversation had changed forever. Cosmology was no longer a philosophical exercise. It became a quantitative science. The distance ladder, once a local tool, became a cosmic instrument. Cepheids calibrated galaxies. Galaxies revealed expansion. Expansion hinted at origins. Each rung carried consequences. In the context of today's Hubble tension, this moment is foundational. The entire debate traces back to Hubble's original insight, that distance and recession are linked, and that measuring that link reveals the universe's behavior. If Hubble had been wrong, none of this would matter. But his conclusion has been tested, refined, and reinforced for nearly a century. The disagreement today is not about whether the universe expands. It is about how fast and what that speed reveals about the ingredients of reality. Hubble did not foresee this tension. He worked with limited data, imperfect calibrations, and early instruments. His original estimate of the expansion rate was dramatically higher than today's values, but the direction was right. He cracked the door open. What followed was a cascade of refinement, correction, and deeper understanding. The universe shrank and expanded on paper as numbers improved, but its fundamental nature remained clear. It is vast. It is dynamic. It has a history. The moment the universe doubled in size was not a moment in cosmic time. It was a moment in human awareness, a shift from a comfortable, contained cosmos to one that extends beyond intuition. That shift still echoes. Every modern measurement of cosmic expansion, every decimal place, every debate, every tension stands on the shoulders of that realization. The universe did not change that day, but from then on, it would never fit inside the same mental boundaries again. Distance in astronomy is never granted. It is earned. By the time Edwin Hubble showed that galaxies lie far beyond the Milky Way, astronomers had accepted a difficult truth. No single method could measure the universe end to end. Distance would have to be assembled, not discovered a structure built from multiple techniques, each extending the reach of the last. This structure became known as the distance ladder. The name is deceptively simple. It suggests something sturdy, something you can climb without fear. In reality, the ladder is a negotiated agreement between methods, assumptions, and evidence. Its strength comes not from certainty, but from cross-checking. Every rung exists because the rung below it has been tested. At the base sits geometry parallax clean, assumption-free, and limited. Above it sit stars whose intrinsic properties can be calibrated using those geometric distances. Above them sit brighter objects that can be seen farther still. Each step reaches deeper into space, but each step also depends on trust. Trust, in science, does not mean belief. It means verification under pressure. When astronomers calibrate a new rung of the ladder, they do not ask whether it works in ideal conditions. They ask how it behaves when conditions are messy, when dust intervenes, when stars crowd together, when environments differ from one galaxy to another. They look for cracks. A trustworthy rung is one that bends but does not break. This is why distance measurement advances slowly. Every extension invites skepticism. Every new technique is treated as provisional until it survives comparison with independent approaches. The ladder is not linear. It is a web of checks and balances. If one rung yields distances slightly larger than another, astronomers do not average them casually. They ask why. Is there a hidden bias, a selection effect, a physical difference between environments, or is one method revealing something real that the other misses? These questions are not academic. They shape the inferred size, age, and expansion history of the universe. Building trust across the ladder requires consistency across scales. Distances measured within the Milky Way must agree with distances inferred in nearby galaxies. Those must align with distances to galaxy clusters. And those, in turn, must be compatible with the large-scale structure of the universe. If a method works only in isolation, it is not enough. This demand for coherence is why the distance ladder has become one of the most scrutinized constructions in science. It is not protected by authority or tradition. It survives because it is constantly challenged. Astronomers recalibrate old data when new measurements appear. They revisit assumptions that were once considered settled. They invite disagreement, because disagreement exposes weakness. Over time, this process has made the ladder remarkably resilient. But resilience does not mean rigidity. As measurements improve, the ladder subtly shifts. Distances are refined. Error bars shrink. Old calibrations are replaced. What remains stable is not the numbers themselves, but the method of testing them. This is crucial for understanding the Hubble tension. The disagreement in the expansion rate did not emerge because someone skipped a step. It emerged because multiple well-tested rungs now extend far enough to overlap, and they do not line up perfectly. That overlap is new. For decades, uncertainties were large enough that differences could be dismissed. As precision improved, those excuses vanished. The ladder became sharp enough to reveal its own internal tensions. This moment is not a failure of trust. It is the result of trust working as intended. When two independent constructions of distance disagree, science does not collapse. It focuses. Astronomers do not rush to declare new physics. They begin by auditing the ladder itself. They examine whether subtle biases might accumulate unnoticed. They ask whether calibration samples are representative. They test whether the same stars behave identically in different galaxies. This forensic approach reflects humility. It acknowledges that the universe is complicated and that measurement techniques, however refined, are human creations. Yet there is a limit to how much uncertainty can be hidden in calibration. At some point, the ladder becomes too tightly constrained to bend without breaking. If every rung is cross-checked and the disagreement persists, attention shifts from measurement to interpretation. That shift is what makes the current moment unusual. The distance ladder has been stress-tested repeatedly. Alternative calibrations have been proposed. Independent teams have reanalyzed the same data with different assumptions. Some adjustments reduce the tension slightly. None remove it entirely. This does not mean the ladder is perfect. It means it is good enough to be taken seriously. Trust, in this context, does not mean confidence that everything is correct. It means confidence that errors, if present, must be subtle, and subtle errors can have profound consequences when multiplied across cosmic scales. The ladder teaches a second lesson as well. Distance is not a property of objects alone. It is a property of relationships. Every rung relates one class of object to another, stars to stars, galaxies to galaxies, light to time. Remove any link, and the chain weakens. This relational nature is why the ladder is vulnerable to hidden correlations. If two methods share an assumption without realizing it, their agreement may be illusory. If they differ fundamentally, their disagreement may be meaningful. Disentangling these possibilities is slow, meticulous work. It requires patience rather than bold claims, repetition rather than novelty. It rewards those willing to revisit foundations rather than chase headlines. The distance ladder, then, is not merely a tool, it is a culture, a way of doing science that values redundancy, skepticism, and incremental improvement. Its strength lies in the fact that it was never meant to be final. Every rung invites replacement. Every calibration is provisional. The ladder is always under construction. In the end, building trust across the distance ladder is not about eliminating uncertainty. It is about understanding where uncertainty lives and how it behaves. The Hubble tension did not appear because trust failed. It appeared because trust succeeded well enough to expose a deeper question. When the ladder is strong and the view still looks strange, the universe is telling you something not loudly, not dramatically, but persistently. And the only honest response is to listen more carefully. There is light around you right now that does not come from the sun, the stars, or any galaxy you can point to. It comes from everywhere, and it comes from almost the beginning of time, long before the first star ignited, long before galaxies formed their spirals. The universe was filled with a dense, blinding fog. Matter and radiation were locked together in a hot plasma. Light could not travel freely. Every photon collided again and again, scattered by charged particles, trapped in an opaque sea. The universe was young, violent, and unreadable. Then, something changed. As space expanded and cooled, that plasma thinned, electrons bound to protons. Neutral atoms formed, and suddenly, almost abruptly, the fog lifted. Light was released. Photons that had been trapped for hundreds of thousands of years were finally free to move in straight lines. That moment left a mark. Those photons are still traveling today. They have been stretched by cosmic expansion, cooled from searing brilliance to a faint microwave glow. They now fill all of space uniformly, arriving at Earth from every direction. This is the cosmic microwave background, the oldest light in the universe. It is not an image of stars or galaxies. It is not a picture in the usual sense. It is a snapshot of the universe when it was less than 500,000 years old, when structure was only beginning to form. To see it is to look as far back as physics allows. At first glance, this ancient light looks almost perfectly uniform. Its temperature varies by only a few parts in 100,000. Wherever you look, the glow is nearly the same. This uniformity is itself astonishing. It tells you that the early universe was remarkably smooth, but it was not perfectly smooth. Hidden within that uniformity are tiny fluctuations, subtle variations in temperature and density. These variations are minuscule, yet they carry enormous meaning. They are the seeds from which all later structure grew. Every galaxy, every cluster, every filament of the cosmic web traces its origin back to these faint irregularities. The cosmic microwave background is not just a relic, it is a record. It encodes information about the universe's composition, geometry, and evolution. The relative amounts of ordinary matter, dark matter, and radiation all leave fingerprints in the pattern of fluctuations. Even the shape of space itself influences how these patterns appear. This is why the oldest light plays such a central role in modern cosmology. By analyzing its structure in exquisite detail, scientists can reconstruct the universe's early conditions and, from there, infer how it evolved into what you see today. But notice the subtlety here. The cosmic microwave background does not directly measure the present-day expansion of the universe. It measures the universe at a specific moment in the distant past. Everything that follows the expansion rate today included is inferred by evolving that early snapshot forward in time using physical laws. This is both powerful and dangerous. It is powerful because the physics of the early universe is relatively simple. Matter and radiation behaved predictably. Complex structures had not yet formed. The equations describing this era are clean and well-tested. It is dangerous because inference always depends on assumptions. To extract today's expansion rate from the oldest light, you must assume you understand how the universe transitioned from that early state to the present one. You must assume no hidden ingredients appeared briefly and vanished. You must assume gravity behaved as expected across billions of years. If those assumptions are correct, the inference is remarkably precise, and the number that emerges is consistent, stable, and stubborn. From the patterns in the oldest light, the universe appears to be expanding more slowly today than local measurements suggest. This conclusion does not arise from a single feature. It emerges from the entire statistical structure of the background, how peaks and troughs align, how scales repeat, how correlations behave across the sky. It is not fragile. It does not wobble easily. That is what makes the tension so unsettling. The cosmic microwave background is not just another data set. It is one of the most carefully measured signals in all of science. Multiple experiments, separated by decades, have observed it with increasing precision. Each improvement sharpened the picture without erasing the discrepancy. The oldest light seems confident in its story, yet that story is indirect. It speaks of a young universe and leaves you to extrapolate. This creates a philosophical contrast with local measurements. Nearby galaxies and stars are messy. Dust obscures them. Environments vary, but they are seen directly, here and now. Their distances are constructed step by step, but the expansion rate emerges from present-day observations. The cosmic microwave background, by contrast, is pristine but distant. It is clean because it comes from a time before complexity. It is remote because everything that matters today happened after it was released. These two approaches complement each other and challenge each other. The oldest light tells you what the universe was like before stars existed. It tells you how much matter there was, how hot space was, how fast everything expanded at that time. It does not tell you whether something subtle happened later. That gap is where the tension lives. If the universe evolved exactly as expected, the early story and the late story should agree. If they do not, then either the measurements are biased or the narrative is incomplete. This is why the cosmic microwave background is not merely evidence, it is a witness. It does not argue, it does not adapt. It simply presents a pattern frozen into space itself. Interpreting that pattern requires humility. The oldest light reminds you that the universe existed long before observers appeared. Its imprint was set without regard for future debates. It carries information, but not intent. When its message disagrees with local measurements, the discomfort comes from confidence, not confusion. Both sides of the comparison are strong. Neither yields easily. The cosmic microwave background also reframes perspective. Everything familiar, stars, planets. Life emerged long after this light was released. When you analyze it, you are not studying the universe as you know it. You are studying the conditions that made everything else possible. In that sense, the oldest light is not about distance or expansion alone. It is about origin. It shows that the universe has a memory, that early conditions matter, that the present is not independent of the past. And when that memory conflicts with present-day measurements, the universe is not contradicting itself. It is revealing that the story connecting then to now may be more complex than assumed. The oldest light does not answer the Hubble tension. It defines one side of it with extraordinary clarity. It tells you how the universe began its expansion. What happened in between remains the open question. When cosmologists extract an expansion rate from the oldest light in the universe, they are not guessing. They are reading a pattern so detailed, so internally consistent, that it behaves like a cosmic blueprint. From the cosmic microwave background, the early universe speaks with a steady voice. It says the expansion today should be slower, not dramatically slower, not in a way that shocks intuition, but slower enough to matter, slow enough to disagree, persistently, with what nearby galaxies appear to show. The value that emerges from this ancient light clusters tightly around one number, roughly 67 kilometers per second per megaparsec. This number is not chosen. It is inferred. It is the consequence of fitting a remarkably simple model to an extraordinarily rich dataset. To understand why this answer carries so much weight, you need to see how it is obtained. The cosmic microwave background is not just a uniform glow. It is structured. Tiny temperature variations form a pattern of peaks and valleys across the sky. These patterns are not random. They encode the physics of the universe at a time when matter and radiation were still tightly coupled. In that early era, the universe behaved like a resonant system. Density fluctuations acted as sound waves moving through a hot plasma. Gravity tried to compress regions of higher density. Radiation pressure pushed back. The result was oscillation. Those oscillations left imprints, the size, spacing, and relative height of the peaks in the microwave background tell cosmologists how fast the universe was expanding at that time, how much matter it contained, how much radiation was present, and how strongly gravity acted. From those ingredients, the entire expansion history can be reconstructed. This is where the key assumption enters. To infer today's expansion rate from early universe data, cosmologists assume that the rules governing cosmic evolution are known and stable. Matter dilutes as space expands. Radiation cools more quickly. Dark energy remains roughly constant. Gravity behaves according to general relativity. Within this framework, the universe's growth from infancy to maturity can be calculated. When this calculation is performed, the result is precise and consistent. Different analyses, different teams, different methods of processing the same early universe signal converge on nearly the same value. The uncertainties are small. The agreement is strong. The early universe, it seems, prefers a slower present-day expansion. What makes this conclusion especially striking is how indirect it is and how robust it remains despite that indirection. The cosmic microwave background does not know what galaxies look like today. It does not encode information about Cepheid stars or supernova explosions. It has no awareness of local structure, and yet, from its faint ripples, a present-day number emerges. This number is not measured directly. It is inferred through a chain of reasoning that spans nearly 14 billion years. And still, it holds together. That coherence is difficult to dismiss. Critics sometimes argue that the early universe answer depends too heavily on a model, that if the model is wrong, the inference could be misleading. This is true in principle. But in practice, the model is not arbitrary. It is constrained by multiple, independent observations. The same framework that yields the slower expansion rate also explains the relative abundance of light elements, the growth of large-scale structure, and the overall geometry of the universe. Adjusting it carelessly to fix one discrepancy risks breaking several other successes. This is the tightrope cosmology walks. If you change the early universe model enough to raise the inferred expansion rate, you must explain why the microwave background still looks the way it does, why its peaks line up, why its statistics remain intact. Small changes are allowed. Radical ones are not. As a result, the early universe answer has acquired a quiet authority. It does not shout. It does not fluctuate wildly. It simply remains. From this perspective, the Hubble tension is not a clash between equal uncertainties. It is a confrontation between a deeply constrained inference and a direct but complex measurement. The early universe number feels almost conservative. It suggests that the universe expanded, slowed under gravity, and then gradually accelerated again under the influence of dark energy, exactly as the standard picture predicts. Nothing exotic is required, and that is precisely the problem. If the early universe answer is correct, then the faster expansion measured locally must be explained. Either distances nearby are subtly miscalibrated, or something happened between then and now that altered the expansion history. The early universe leaves little room for improvisation. This creates a psychological asymmetry. The early universe measurement feels clean, detached, and universal. The local measurement feels tangled in astrophysical detail. It is tempting to trust the former more than the latter. But temptation is not evidence. The early universe answer rests on the assumption that nothing unexpected intervened during cosmic evolution. That assumption has been extraordinarily successful, but success does not guarantee completeness. History offers a cautionary lesson. Physics has often encountered situations where well-tested theories worked beautifully until a small anomaly forced reconsideration. Mercury's orbit, blackbody radiation, the photoelectric effect. In each case, The old framework was not discarded wholesale. It was extended. The Hubble tension may belong to this lineage, or it may dissolve with better calibration. At this stage, both possibilities remain open. What the early universe answer does is narrow the field. It tells you that if new physics exists, it must be subtle. It must respect the microwave background structure while altering the later expansion just enough to reconcile the numbers. This is a demanding requirement. The early universe is not easily fooled. Its light has been traveling since before stars existed, carrying with it a record of conditions that are difficult to rewrite retroactively. That is why this slower expansion rate matters so deeply. It is not just a number. It is a consistency check on our understanding of cosmic history. It is the universe saying, given what I was, this is what I should be now. It's when the present does not match that expectation. The discomfort is not mathematical, it is conceptual. Either the inference is incomplete, or the universe changed its behavior in a way not yet recognized. The early universe answer does not tell you which is true. It simply refuses to go away, and in that refusal lies its power. If the early universe offers a carefully reconstructed prediction, the local universe offers a direct report. This report comes not from ancient light, but from nearby stars and galaxies, objects you can study in detail, revisit, and cross-check. It is assembled step by step, rung by rung, using the distance ladder built from geometry, stellar behavior, and cosmic explosions. And when that ladder is climbed carefully, it delivers a different message. The local universe says the expansion today is faster, not by a dramatic margin, but by enough to matter, enough to persist, enough to refuse reconciliation with the early universe answer. The value that emerges from local measurements consistently lands near 73 kilometers per second per megaparsec. Like its slower counterpart, this number is not casual. It is the result of decades of refinement, recalibration, and scrutiny to understand why the local universe speaks this way. It helps to follow the measurement from the ground up. It begins with parallax pure geometry, measuring distances to nearby stars by observing their apparent shift as Earth moves around the Sun. These measurements anchor the scale. They are the bedrock. From parallax-calibrated stars, astronomers move to Cepheid variables, pulsating stars, whose intrinsic brightness can be inferred from their rhythm. By comparing how bright these stars appear to how bright they truly are, distances to nearby galaxies become measurable. Then comes the crucial leap. Some of those galaxies also host a different kind of beacon, type Ia supernovae. These are stellar explosions of remarkable uniformity. When they occur, they briefly outshine entire galaxies, making them visible across hundreds of millions of light years because their peak brightness follows a predictable pattern. Type Ia supernovae act as extraordinarily bright standard candles. Cepheids calibrate them. Supernovae extend the ladder outward. Once distances to many galaxies are known, their redshifts, the stretching of their light, are measured. Plot distance against redshift, and the slope reveals the expansion rate. This process is not performed once. It is repeated across many galaxies, many environments, many datasets. Different teams use different instruments, different analysis pipelines, different calibration strategies. The result remains. The nearby universe expands faster than the early universe predicts. What gives this conclusion weight is not just repetition, but transparency. Local measurements expose their assumptions openly. Astronomers know where dust dims starlight. They know where stellar crowding blurs images. They correct for these effects explicitly, often in multiple ways. The uncertainties are catalogued. The biases are hunted. Critics sometimes imagine that the local measurement is fragile because it relies on astrophysical objects rather than pristine early universe physics. In reality, that complexity is both a challenge and a strength. Stars and supernovae are messy, but they are observable. They can be studied in different wavelengths. They can be compared across environments. Their behavior can be tested repeatedly. When discrepancies arise, they do not hide easily. This is why the faster expansion rate has survived so many attempts to dismantle it. When distances are recalibrated using updated parallax data, the value shifts slightly but not enough. When dust corrections are refined, the uncertainty shrinks but the number remains high. When alternative stellar populations are used, the result persists. The local universe, like the early universe, seems confident in its story. This creates an uncomfortable symmetry. On one side, a clean, ancient inference filtered through a well-tested model. On the other, a direct, present-day measurement assembled from carefully calibrated observations. Both are precise. Both are consistent within themselves. Neither yields. The faster expansion rate carries a different philosophical weight than the slower one. It is grounded in the here and now. It measures the universe as it currently behaves, not as it once did. If something changed along the way, if the universe evolved in an unexpected manner, local measurements would be the first to notice. This is why some scientists view the local result not as an anomaly, but as a warning, a hint that the cosmic expansion history may include subtleties not captured in the simplest picture. But caution cuts both ways. Local measurements depend on a chain of calibrations. Each rung is well tested, but the ladder as a whole is still a construction. A small systematic error shared across multiple rungs could, in principle, bias the result. The difficulty lies in identifying such an error without breaking the internal consistency of the ladder. So far, no single adjustment has succeeded. This is what elevates the Hubble tension, from technical dispute to conceptual challenge. It is not a matter of one bad measurement versus one good one. It is a confrontation between two mature methods that should agree and do not. The local universe does not merely report a faster expansion. It does so with increasing confidence as data improves. That confidence is unsettling because it narrows the space for easy explanations. If the local measurement is wrong, the error must be subtle, coherent, and elusive. If it is right, then something in the standard cosmic narrative is missing. Neither option is comfortable. The faster expansion rate also has implications that ripple outward. It suggests a younger universe, a different growth rate for cosmic structure, and potentially altered properties for dark energy. These are not cosmetic changes. They affect how galaxies form, how matter clusters, and how the future unfolds. Yet the local measurement itself remains humble. It does not claim to explain why the expansion is faster. It only reports what the nearby universe appears to be doing. This restraint is important. The local universe does not argue. It presents evidence. It leaves interpretation to theory. In the end, the faster expansion rate is not a challenge to cosmology. It is a demand placed upon it. It says, if your story of the universe is complete, it should account for what is observed now, not only what is inferred from the distant past. The early universe tells one story. The local universe tells another, and both stories are written in light. In science, disagreement is not unusual. What is unusual is when disagreement survives precision. For most of history, cosmological measurements disagreed because they were crude. Telescopes were small, data was sparse, error bars were wide enough to overlap generously. Differences could be blamed on noise, technique, or incomplete understanding. That is not what is happening here. The Hubble tension exists precisely because measurements have become too good to ignore one another. Both sides of the debate, the early universe inference and the local universe measurement, operate at a level of precision that would have been unthinkable a generation ago. Each has been refined, cross-checked, and stress-tested. Each reports uncertainties small enough that their results should overlap. They do not. This is the point where disagreement stops being a nuisance and starts becoming a signal. Precision is supposed to clarify. When it doesn't, something deeper is at work. To appreciate why this moment is so uncomfortable, consider how scientists normally respond to conflicting results. They look first for error. They check instruments. They reanalyze data. They search for hidden biases. Most of the time, this process works. Disagreements shrink. Consensus emerges. Here, the opposite has happened. As measurements improved, the gap did not close. It sharpened. This sharpening changes the character of the problem. It removes the safety net of uncertainty. You can no longer shrug and say, "The numbers will converge eventually." Eventually has arrived, and convergence did not. In statistical terms, the disagreement has grown too large to dismiss casually. In human terms, it has become awkward. The universe appears to be answering the same question in two different ways. That forces a re-examination of what precision actually means. Precision is not the same as truth. A measurement can be precise and still wrong if it rests on flawed assumptions. But when two independent measurements are both precise and both carefully scrutinized, the odds that one is grossly mistaken diminish. This is what elevates the Hubble tension above routine dispute. The early universe measurement relies on a global fit to an ancient signal, constrained by fundamental physics. The local measurement relies on a chain of calibrations grounded in direct observation. Their methodologies share little overlap. Their errors are unlikely to be correlated, and yet they disagree. This is not the kind of disagreement that can be resolved by averaging the results. Averaging assumes that the measurements are sampling the same underlying quantity with random error. Here, the errors are systematic, directional, and method-dependent. You cannot split the difference and call it progress. Instead, disagreement becomes diagnostic. When precision measurements disagree, the universe is not being capricious. It is exposing the boundaries of understanding. It is revealing where models stop being explanatory and start being approximations. This is a familiar pattern in the history of physics. The orbit of Mercury disagreed slightly with Newtonian predictions. The discrepancy was tiny, almost negligible, but it persisted. It refused correction. That refusal eventually led to general relativity. The spectrum of blackbody radiation disagreed with classical theory. The mismatch was subtle at first. Precision made it unavoidable. Quantum mechanics followed. In each case, the disagreement was not large. It was precise. The Hubble tension sits uncomfortably in this tradition. That does not mean it will lead to a revolution. Many tensions dissolve with improved understanding. But it does mean it deserves attention, not dismissal. What makes this moment especially delicate is that cosmology has enjoyed extraordinary success. The standard model of the universe explains a vast array of observations with remarkable economy. It has survived decades of scrutiny. This success creates inertia. When a theory works well, the instinct is to protect it. Discrepancies are assumed to be mistakes until proven otherwise. That instinct is rational. It prevents overreaction, but it can also delay recognition. Precision disagreement challenges that instinct gently but persistently. It asks whether success in many areas guarantees completeness in all. The Hubble tension does not shout that the model is wrong. It whispers that the model may be incomplete. This whisper is easy to ignore. It is tempting to believe that one more calibration, one more correction, one more dataset will restore harmony. That hope has motivated years of careful work. So far, harmony has not returned. This does not imply failure. It implies honesty. When precision measurements disagree, the correct response is not to choose a winner, but to widen the lens, to ask whether the question itself is being framed too narrowly, to examine whether unseen assumptions are shaping interpretation. It also requires restraint. Scientific history is littered with anomalies that inspired grand speculation, only to fade with better data. The challenge is to hold tension without rushing to resolution. This balance between openness and skepticism is difficult to maintain. On one side lies complacency, the belief that everything important is already known. On the other lies sensationalism, the urge to declare new physics at the first sign of trouble. The Hubble tension lives in the narrow space between those extremes. Precision disagreement is not an alarm bell. It is a pressure gauge. It tells you that something in the system is under strain. Whether that strain reflects measurement limits or missing physics remains to be seen. What cannot be denied is that the disagreement is real. Two answers persist. Both are supported by careful work. Neither can be waved away. This forces a philosophical shift. Instead of asking, which number is correct, the more productive question becomes, why do these methods disagree at all? That question reframes the problem from a conflict to an opportunity. When measurements disagree, they point toward blind spots. They highlight where models simplify too aggressively. They reveal where assumptions hide. In that sense, disagreement is not an obstacle to progress. It is its engine. The universe does not owe consistency to our expectations. It only owes consistency to itself. When our most precise tools fail to agree, the failure is not theirs alone. It belongs to the framework that connects them, and frameworks can evolve. Precision has carried cosmology to the edge of its confidence. Beyond that edge lies either a correction, small but consequential, or an expansion of understanding. For now, the disagreement stands, not as a verdict, not as a crisis, but as a quiet, persistent reminder that even the most careful measurements can reveal how much remains unfinished. When measurements disagree, science does not accuse the universe. It interrogates itself. Before invoking new forces or rewriting cosmic history, astronomers turn to the most ordinary explanation available. Systematic error, not random noise, not sloppy work, but subtle, persistent biases that slip through careful procedures and affect results in the same direction. Again and again, systematic errors are the first suspects because they are the hardest to see. Random errors average out. Collect enough data and they fade. Systematic errors do the opposite. They hide inside methods, instruments, and assumptions, quietly steering conclusions while appearing consistent. In the case of the Hubble tension, the search for systematic error has been relentless. Every rung of the distance ladder has been examined under harsh light. Every correction has been questioned. Every calibration has been challenged. The goal is not to defend a preferred number, but to discover whether the disagreement can be explained without changing the underlying story of the universe. The investigation begins close to home. Parallax measurements, geometry's gift to astronomy, are scrutinized first. Space-based observatories have pushed parallax precision to astonishing levels. But even tiny biases matter when they anchor the entire ladder. Astronomers examine detector behavior, orbital modeling, data reduction pipelines, and statistical assumptions. If parallax distances drift even slightly, every higher rung inherits the shift. So far, no hidden bias large enough to explain the tension has been found. Next come Cepheid stars. These pulsating stars are powerful tools, but they live in complex environments. Dust dims light. Nearby stars blend together. Chemical composition varies from galaxy to galaxy. Each factor can subtly alter the inferred brightness of a Cepheid and, therefore, its distance. Astronomers attack these problems methodically. They observe Cepheids in infrared light, where dust has less effect. They compare Cepheids in different host galaxies. They separate samples by metallicity and age. They use multiple instruments and independent analysis techniques. The results change details, but not the conclusion. Type Ia supernovae face similar scrutiny. Though often described as standard candles, they are not perfectly uniform. Their brightness depends on how they are corrected and standardized. Selection effects can bias samples toward brighter explosions. Host galaxy properties can influence observed behavior. Again, these effects are known. They are modeled, corrected, and tested. Independent teams repeat analyses with different assumptions. No single correction erases the discrepancy. At this point, skepticism deepens. If each rung appears robust on its own, perhaps the problem lies not in individual steps, but in how they are combined. Perhaps subtle correlations exist between calibrations. Perhaps assumptions shared across methods amplify small biases. This possibility is taken seriously. Astronomers perform blind analyses, withholding key parameters until procedures are finalized. They cross-calibrate using alternative anchors. They compare results using different stellar populations and different cosmic environments. The goal is not to prove correctness, but to expose vulnerability. On the other side of the tension, early universe measurements are also examined for systematic effects. The cosmic microwave background is measured with extraordinary care, but interpreting it requires modeling, instrument noise, foreground contamination, beam calibration, and data processing choices all matter. The influence of galactic dust, extragalactic sources, and instrumental artifacts must be removed with precision. Cosmologists test whether small changes in these procedures could bias the inferred expansion rate. The answer, so far, is discouraging for easy explanations. To significantly alter the early universe result, one must change assumptions that also affect other observables, features of the microwave background that are measured independently and agree with predictions. Tweaking one part of the model tends to break another. Systematic error remains possible, but it must be unusually subtle. This is where discomfort grows. Systematic errors are comforting suspects because they preserve the existing framework. They suggest that the universe is behaving as expected and that the disagreement reflects human limitation rather than cosmic surprise. But the longer a systematic error evades detection, the more suspicious that explanation becomes. In science, the absence of evidence is not evidence of absence, but persistent absence carries weight. The Hubble tension has survived years of scrutiny across multiple independent teams, instruments, and methodologies. That does not eliminate systematic error as a possibility. It narrows it. Any remaining bias must be coherent across datasets, resilient to reanalysis, and finely tuned to produce the observed discrepancy without revealing itself elsewhere. Such errors exist, but they are rare. This realization forces a shift in mindset. Systematic errors are no longer treated as obvious culprits. They become hypotheses that must work harder to justify themselves. Each proposed bias is examined not only for plausibility, but for consistency with everything else that is known. At this stage, skepticism cuts in both directions. Skepticism of measurement demands that astronomers continue searching for hidden biases. Skepticism of theory demands openness to the possibility that the framework itself may need refinement. Neither position is comfortable. To accept a systematic error without identifying it feels intellectually unsatisfying. To invoke new physics without exhausting known explanations feels premature. The tension between these instincts mirrors the cosmic tension itself. There is also a deeper lesson here. Systematic errors are not mistakes. They are reminders that measurement is not passive. Every observation is filtered through instruments, choices, and models. Precision does not eliminate interpretation. It sharpens its consequences. The history of science is filled with cases where systematic errors delayed discovery, and others where apparent errors concealed new truths. The challenge is distinguishing between the two in real time. In the present case, the systematic error hypothesis remains alive, but constrained. It no longer serves as a catch-all explanation. It demands specificity. Which bias? Where exactly does it enter? Why does it affect one method but not others? Until those questions are answered convincingly, the suspect remains unproven. Systematic errors were the first suspects because they are the most conservative explanation. They protect the existing picture of the universe. They preserve continuity. But conservatism alone is not a solution. Science advances not by choosing the most comfortable answer, but by following evidence where it leads, even when that path is narrow, uncertain, and unsettling. For now, the systematic errors remain under interrogation. They have not been cleared. They have not been convicted. They stand in a growing lineup of possibilities, waiting to be either exposed or surpassed by a deeper explanation. When two primary measurements disagree, science looks for witnesses, not accomplices, not echoes of the same assumptions, but independent lines of evidence, methods that ask the same question in a different language, with different tools and different vulnerabilities. In the case of cosmic expansion, these independent witnesses occupy a crucial role. They do not replace the early universe inference or the local distance ladder. They stand alongside them, offering testimony that can either reinforce one side, soften the tension, or complicate the story further. The first of these witnesses emerged from a simple idea. Not all stars age and behave the same way. Cepheid variables are powerful rulers, but they are not the only ones. Another stellar population, older, quieter, and less flashy, offers an alternative route to distance. These stars live at the tip of the red giant branch. As low-mass stars exhaust their nuclear fuel, they swell into red giants. At a particular point in their evolution, their brightness reaches a predictable maximum before changing behavior. This cutoff is remarkably consistent across different environments. Unlike Cepheids, these stars are ancient. They populate old stellar systems where star formation has long since ended. Their environments are simpler. Their physics is well understood. Using the brightness of this red giant branch tip as a distance indicator provides a separate calibration of nearby galaxies, one that does not rely on Cepheid pulsations. When this method is applied and extended outward using supernovae, the inferred expansion rate tends to land between the two main values, not as slow as the early universe prediction, not as fast as the Cepheid-based ladder. This does not resolve the tension, it sharpens it. A middle value suggests that distance calibration may be more subtle than assumed. It hints that different stellar populations may encode distance in slightly different ways, or that no single ruler tells the full story. Another independent witness comes not from stars at all, but from gravity. In some galaxies, massive foreground objects bend space-time strongly enough to distort the light from more distant sources behind them. When the alignment is right, this gravitational lensing produces multiple images of the same object. If that background object varies in brightness, such as a quasar, the changes appear in each image at different times. The delays depend on the geometry of space, the mass distribution of the lens, and the expansion rate of the universe. Measure those delays carefully, model the lens accurately, and the expansion rate can be inferred. This method shares almost nothing with the distance ladder or the cosmic microwave background. It relies on general relativity, geometry, and time delays. Its results tend to favor a faster expansion, closer to the local measurement, but the uncertainties remain larger. Modeling the mass distribution of lensing galaxies is complex. Small assumptions can shift results. The witness speaks, but with a cautious voice. Still, Its testimony matters. A third, even younger witness is beginning to emerge, one that does not rely on light at all. When massive objects like neutron stars collide, they send ripples through space-time itself. These gravitational waves carry information about the system's absolute scale. The strength of the signal reveals how far away the event occurred. If the host galaxy can be identified and its redshift measured, the expansion rate can be inferred directly without a distance ladder. These events are called standard sirens. They are rare. The data is limited. The uncertainties are large. But the method is clean in principle. It bypasses many of the assumptions that plague traditional techniques. Early results are consistent with a wide range of expansion rates. They do not yet favor one side decisively, but they promise something important. They promise a future in which the universe can be measured using its own vibrations, rather than the light of its contents. Each of these witnesses adds texture to the debate. None overturns the main results. None resolves the tension outright. But together, they show that the disagreement is not confined to a single flawed method. Different approaches, with different strengths and weaknesses, point in different directions. This diversity of testimony complicates the narrative, but also strengthens it. If all independent methods agreed perfectly, there would be little to discuss. If they all failed in the same way, systematic error would be the obvious culprit. Instead, the witnesses disagree among themselves. That is uncomfortable. It is also revealing. It suggests that the expansion rate is not a simple quantity extracted cleanly by any one method. It is a parameter woven into cosmic history, sensitive to details that different techniques probe differently. Some methods are anchored in the early universe. Others live entirely in the present. Some rely on stellar physics. Others depend on space-time geometry. Each sees a different facet of the same phenomenon. The role of independent witnesses is not to deliver a verdict. It is to constrain the possibilities. They narrow the space in which explanations can hide. They rule out easy fixes. They demand coherence across methods that share little in common. In doing so, they elevate the tension from a dispute between two camps into a broader inquiry about how the universe reveals itself. The expansion of space is not a single event. It is a process unfolding across billions of years. It is influenced by matter, radiation, gravity, and energy in ways that may not be fully captured by simplified models. Independent witnesses remind you of that complexity. They also remind you of something else. Science does not progress by unanimity. It progresses by convergence, slow, careful, and often frustrating convergence toward a story that can accommodate all reliable evidence. Right now, convergence has not yet occurred. The witnesses are still speaking. The data is still accumulating. The uncertainties are shrinking, but not disappearing. What remains is a landscape of partial agreement and persistent tension. That landscape is not a failure of method. It is the natural terrain at the frontier of understanding. Independent witnesses do not bring closure. They bring depth. And in the space between their testimonies, the universe continues to expand, measured, questioned, and quietly unresolved. When measurements refuse to agree and systematic errors grow elusive, science reaches a delicate crossroads. This is where the phrase new physics enters the conversation. It is not spoken lightly. Invoking new physics is not an admission of failure. It is an acknowledgement that the current framework, however successful, may not be the final word. History shows that the most transformative advances often begin this way, not with dramatic contradictions, but with small, persistent mismatches that refuse to fade. The Hubble tension sits precisely in that uncomfortable space. The standard picture of the universe works extraordinarily well. With a handful of ingredients, ordinary matter, dark energy, and gravity, it explains the growth of structure. The the cosmic microwave background, the abundance of light elements, and the large-scale geometry of space. That success creates resistance to change. Any new physics proposed to resolve the tension must be subtle enough to preserve everything that already works, while still altering the expansion history just enough to reconcile the numbers. This is a narrow path. Most ideas fail immediately, yet a few possibilities continue to be explored not because they are fashionable, but because they survive confrontation with data. One class of ideas focuses on the early universe. If something briefly altered the energy balance shortly after the cosmic microwave background was formed, it could change how the universe expanded without leaving obvious scars elsewhere. These scenarios introduce additional energy components that were present only temporarily, often described as early dark energy. These ideas suggest that a small amount of extra energy accelerated expansion for a short period, then faded away. The universe would then settle into the familiar evolution seen today. This kind of intervention could shift the inferred expansion rate from early universe data, while leaving present-day physics largely untouched. The appeal of such models is their restraint. They do not overhaul gravity. They do not invent exotic forces that act today. They insert a brief chapter into cosmic history, then close it quietly. The challenge is consistency. Any extra energy must leave the cosmic microwave background nearly unchanged. It must preserve the observed pattern of fluctuations. It must not disrupt the formation of galaxies. Each requirement narrows the allowed behavior. So far, these models remain plausible but constrained. Another possibility involves particles rather than energy. The early universe was a hot, dense environment where even slight changes in particle content could have lasting effects. If additional light particles existed, ones that interacted weakly and escaped detection, they could alter the expansion rate at early times. Neutrinos already play such a role. Adding more neutrino-like species, or modifying their behavior, changes the early expansion subtly. These ideas tread carefully around known physics. They extend what already exists rather than inventing entirely new mechanisms. Yet here, too, data pushes back. Measurements of the cosmic microwave background and large-scale structure limit how many extra particles can be added without spoiling agreement elsewhere. The room for maneuver is small. Then there are ideas that question gravity itself. General relativity has passed every test thrown at it within the solar system and beyond. But cosmology probes gravity on the largest scales imaginable. Across the entire history of the universe, some theorists explore whether gravity behaves slightly differently over cosmic distances or times, not in ways that would affect planetary orbits or black holes, but in ways that influence the overall expansion. These modifications are subtle by necessity. Any deviation must reduce to familiar gravity in known regimes. Such ideas are mathematically intricate and observationally demanding. They also carry philosophical weight. Gravity is not just another force, it is the geometry of space-time itself. Altering it is never done casually. A more conservative interpretation of new physics is not new laws, but incomplete understanding. Dark energy, for example, is often treated as a constant background property of space, but its true nature remains unknown. If dark energy evolves over time, even slightly, it could affect the expansion history without violating existing constraints. In this view, the Hubble tension is not evidence of exotic phenomena, but of oversimplification. The universe may be doing something modest yet unfamiliar, something that does not announce itself loudly, but accumulates consequences over billions of years. What unites all these possibilities is caution. None of them claim victory. None offer a clean, decisive solution. Each proposal is tested not only against the Hubble tension, but against everything else the universe has revealed. This is why progress is slow. New physics cannot be bolted on. It must integrate. The temptation to leap toward radical conclusions is strong. A discrepancy invites imagination. But cosmology has learned restraint the hard way. For every anomaly that reshaped understanding, many more dissolved with patience. The Hubble tension has not yet crossed that threshold. It remains an invitation rather than a verdict. That invitation carries a philosophical undertone. Physics progresses by discovering limits. Every theory describes a domain where it works, not an absolute truth. Newton's laws did not fail, they were surpassed. Classical physics did not collapse, it was expanded. The standard cosmological model may be similar, profoundly useful, deeply accurate, and still incomplete. New physics, if it emerges here, is unlikely to be dramatic. It will not overthrow what is known. It will refine it. It will add a sentence, not rewrite the book. This perspective tempers expectation. The possibility of new physics does not promise revelation on demand. It demands rigor, humility, and patience. It requires accepting that the universe may not yield its secrets quickly or neatly. At this stage, the most honest position is openness without commitment. The tension has persisted long enough to merit exploration beyond known explanations. It has not yet justified abandoning them. Science does not reward haste. It rewards endurance. Whether the Hubble tension signals new physics or unresolved measurement remains undecided. But the willingness to ask that question, to entertain the possibility without declaring it, is itself a mark of healthy inquiry. The universe does not owe clarity. It offers clues, and sometimes those clues point not to what is wrong, but to what is missing. A model is not a mirror of reality. It is a tool for navigating it. The cosmological model you rely on today is a compact description of a vast universe. With a small set of assumptions, it connects the early glow of the cosmos to the distribution of galaxies, the abundance of elements, and the large-scale geometry of space. It is efficient, it is predictive, and it has earned trust by working across an extraordinary range of evidence. The Hubble tension does not topple this model. It presses on it. That pressure matters. A healthy model bends under scrutiny without breaking. It reveals where its assumptions are tight, where they are loose, and where they may be oversimplified. The tension forces precisely this kind of audit. At the heart of the model lies a narrative of cosmic growth. Space expands. Matter slows that expansion. Dark energy accelerates it later. The sequence is smooth and continuous, governed by stable laws. From this story, a present-day expansion rate follows naturally from early conditions. The early universe inference aligns beautifully with that narrative. The local measurement does not. This mismatch does not say the model is wrong. It says the model is being asked a sharper question than before. For decades, uncertainties were large enough that the model's predictions could accommodate a wide range of values. Precision has changed that. Now, the model must choose. It cannot be everything to everyone. What does it mean when a model that explains so much struggles with one parameter? First, it means the model's success elsewhere is real. The tension exists because the model is constrained. If it were flexible, the discrepancy could be absorbed easily. Instead, the model's rigidity makes the disagreement visible. Second, it means assumptions once considered harmless are now consequential. In cosmology, assumptions are often global. You assume gravity behaves the same everywhere. You assume dark energy is constant. You assume the early universe transitioned smoothly into the later one. These assumptions are reasonable and supported, but they are still assumptions. The Hubble tension tests their limits. If the model is complete, the disagreement must come from measurement. If the measurements are sound, the model must adapt. Either outcome refines understanding. This is not a crisis. It is a calibration of confidence. There is also a deeper implication. The model may be correct in structure, but incomplete in detail. History suggests this pattern is common. The laws of motion worked until precision exposed anomalies. Classical electromagnetism worked until radiation behavior forced reconsideration. In each case, the older theory remained useful within its domain, even as it was extended. The cosmological model may be at a similar threshold. The Hubble tension does not demand a new universe. It may demand a better description of this one. Consider what the model currently treats as fixed. Dark energy is assumed to be uniform and unchanging. That assumption simplifies equations and matches many observations. But it is not derived from first principles. It is a placeholder for an effect that is measured, not understood. If dark energy evolves slightly with time, the expansion history changes subtly. The early universe would infer one value. The local universe would measure another. Both could be correct within their contexts. This would not overthrow the model. It would enrich it. Similarly, the model assumes that the contents of the universe behaved in a straightforward way after the release of the oldest light. Matter cooled. Structures grew. Nothing unexpected intervened. But cosmology rarely rewards absolute certainty. A brief episode, a small interaction, a short-lived component, any of these could alter expansion, just enough to matter, without leaving glaring contradictions elsewhere. The tension invites exploration of such possibilities, not as acts of desperation, but as acts of completion. There is also a sociological aspect to what this tension means. Models gain authority through success. That authority shapes expectations. When data conflicts with expectation, the initial reaction is often defensive. This is not a flaw. It is a safeguard. It prevents overfitting reality to every anomaly. But prolonged tension shifts the balance. When disagreement persists across years and methods, the burden of proof slowly redistributes. The model is no longer the unquestioned baseline. It becomes one hypothesis among others, albeit a very strong one. This shift is subtle, but important. It marks a transition from confirmation to interrogation. The Hubble tension does not say, "Your model is wrong." It asks, "How complete is your model?" Really? That question has practical consequences. Cosmological parameters are not isolated numbers. They influence estimates of the universe's age, the timing of structure formation, and the future behavior of space itself. A higher expansion rate implies a younger universe and alters the growth of galaxies. A lower rate implies a longer timeline. If the model misjudges this parameter, even slightly, interpretations ripple outward. But ripple is not collapse. The model remains an extraordinarily good approximation. It continues to guide observation, simulation, and theory. The tension simply signals that approximation has reached a resolution limit. Beyond that limit, refinement is required. Importantly, the tension also demonstrates the maturity of cosmology. You are no longer arguing about orders of magnitude. You are arguing about a few kilometers per second per megaparsec. That is not ignorance. That is precision revealing nuance. This maturity allows for a different kind of humility. Instead of asking whether the model is right or wrong, you begin asking where it is silent, where it assumes rather than explains, where it simplifies for tractability. Those silences are opportunities. They do not diminish the model's achievements. They define the frontier of its relevance. The Hubble tension, then, is not a verdict on cosmology. It is a stress test, one that the model is mostly passing, but not perfectly. And that imperfection is instructive. It reminds you that models are maps, not territories. They guide exploration, but they are revised as terrain becomes clearer. The better the map, the more obvious its limitations become. In this sense, the tension is a sign of progress. It means the universe is no longer hiding behind noise. It means measurements are sharp enough to challenge assumptions. It means cosmology has moved from broad strokes to fine structure. Whether the model absorbs the tension through better calibration or evolves to include new ingredients, its role remains the same: to organize understanding, not to freeze it. The universe has not changed, but the questions you are now able to ask have, and that is what the Hubble tension truly means for the cosmic model you trust, not that it has failed, but that it has carried you far enough to see where it must grow. At the end of all the measurements, all the arguments, all the carefully drawn diagrams and refined numbers, something quieter remains. Humility, not the kind that diminishes human effort, but the kind that gives it meaning. The Hubble tension does not confront you with chaos. It confronts you with a boundary, a place where understanding slows, where confidence gives way to caution, and where certainty must be earned rather than assumed. This boundary is not new. Science has encountered it many times before. What is new is how clearly it now comes into focus. For centuries, the universe resisted measurement altogether. Distances were guessed. Motions were debated. The cosmos was more philosophy than physics. Today, you measure expansion to a few percent. You argue not about whether the universe expands, but how fast, and why different methods disagree. That shift alone is extraordinary. It is tempting, at moments like this, to demand closure, to insist that the universe provide a single, clean answer. But nature does not work on deadlines, and understanding is not delivered on command. The tension exists because you now know enough to see it. Earlier generations could not. Their tools were too blunt, their uncertainties too wide. They lived comfortably inside ignorance without realizing it. You do not. You live at a moment when precision has pushed knowledge to its edge. Beyond that edge lies ambiguity, not because the universe is inconsistent, but because your descriptions are still incomplete. This realization carries a quiet lesson. Human understanding does not advance by conquering mystery, but by narrowing it. Each resolved question exposes deeper ones. Each refined measurement reveals subtler discrepancies. Progress does not simplify reality. It complicates it carefully, usefully. The Hubble tension is one such complication. It does not shout that the universe is broken. It whispers that your story about it may be unfinished. That whisper is easy to ignore. It does not disrupt daily life. It does not rewrite textbooks overnight, but it lingers. And lingering questions shape the future more than loud answers. There is also a moral dimension to this humility. Cosmology deals in extremes, billions of years, unimaginable distances, energies far beyond human experience. In that context, it would be easy to feel insignificant. Yet the opposite is true. The fact that you can even notice a discrepancy in the universe's expansion rate is a testament to collective human curiosity, to centuries of observation, debate, correction, and patience, to a willingness to accept uncertainty rather than hide it. Humility here is not weakness, it is discipline. It is the discipline to resist premature explanations, to hold competing ideas in balance, to accept that the most honest answer, sometimes, is we do not yet know. I'm sowed. This discipline is rare and valuable. At the edge of cosmic knowledge, arrogance fails quickly. Grand claims collapse under scrutiny. What survives is careful reasoning, incremental progress, and openness to revision. The universe does not reward confidence. It rewards accuracy. The Hubble tension also reframes humanity's place in the cosmos. You are not observers standing outside the universe, measuring it from a safe distance. You are inside it, made of the same matter, governed by the same laws, carried along by the same expansion you are trying to measure. Your instruments move with the cosmos. Your clocks tick within it. Your theories are shaped by perspectives that are unavoidably local. Recognizing this does not invalidate measurement. It contextualizes it. It reminds you that all knowledge is situated, that objectivity is approached asymptotically, never reached absolutely, that every cosmic number is filtered through human choice. interpretation, and limitation. And yet, despite these limitations, understanding advances. The expansion of the universe was once unimaginable, its measurement once impossible, its tension once invisible. Each step required imagination, persistence, and humility. There is no reason to believe the next step will be easier. Whether the Hubble tension ultimately dissolves into refined calibration or matures into new physics, its role is already clear. It has done what the best scientific problems do. It has slowed certainty and sharpened inquiry. It has reminded you that even the most successful models are provisional, that even the most elegant explanations must submit to data, that the universe is under no obligation to be simple. At this edge, humility becomes a guiding principle. It encourages listening rather than declaring, testing rather than assuming, revising rather than defending, and perhaps most importantly, it preserves wonder. The universe is not a puzzle to be solved once and set aside. It is an ongoing conversation between what exists and what can be understood. Each answer changes the question. Each measurement deepens the mystery. Standing here, with two numbers still unresolved, you are not witnessing failure. You are witnessing science doing exactly what it is meant to do, learning where its knowledge ends